Maybe we can get started. So welcome again to the session 5 of APPROX. The first talk of this session will be by Theopile Theory on improved multipass streaming algorithms for submodular maximization with matroid constraints. So Theopile, please go ahead.
Yes, thanks. So do you see the screen well?
Yeah, looks good.
So I'm going to talk about improved multipass streaming algorithm for submodular maximization with matroid constraints. This is a joint work with Chen-Chong Huang and Justin Ward. Yeah, so as you may already be familiar, we are looking at maximizing a submodular function f. So submodular functions are just set functions which satisfy this following diminishing return property. And the goal is to maximize them, and we want to return a set S that satisfies some constraints that belongs to this calligraph I, which is a constraint on the allowed set that I'm allowed to return. And in this work, we focus mostly on the p-matroid constraint. But this constraint is not really specific. It's just generalizes intersection of p-matroid and matroid. And an example of a p-matroid, you can think of matchings that are just two matroid. I can discuss the detail later. So just I always assume that the function is positive, but I'm not necessarily assuming that the function is monotone, which are common assumption in the literature. So the setting we're considering is a multipass streaming setting. So it is motivated by, let's say, machine learning application where you want to summarize a video or, let's say, a bunch of research paper, and you want to build a summary that contains valuable information. And instead of looking at the video or the research paper once, you are able to look at it several times to improve, let's say, your summary. So in a document summarization task, the sentences or elements arrive on the fly, and you have a limited memory, which is typically poly K, and the stream can be adversarial. So we don't assume any specific distribution on the stream. And when we see an element, either we discard it or we store it in the memory. The difference with the online model is that we can select our elements and not necessarily put it in our final solution. So the main result that we get for this problem for monotone submodular function f is that under a p-matroid constraint and a monotone function f, we have a p+1 approximation that processes the stream roughly p over epsilon times. This directly gives us a 2 plus epsilon approximation in 2 over epsilon passes under a matroid constraint. So how does this relate to current result? Well, the best known result for, we know the best we can do so far is 1 over p+1 plus epsilon in roughly log square n passes. And we managed to remove the dependence on n. The best we can do for a single pass is this 1 over 4p, but it isn't known, it's probably not timed. So there is also some results in our paper, which I won't mention here because it relates to either constraints that fall under p-matroid or non-monotone submodular functions. And we also show that, for example, if we don't do p over epsilon passes, but let's say 2 passes, we also get some improvement. So how do we proceed to get those results? Well, I won't be able to give you the whole proof, but let me give you just some brief intuition. So we run streaming local search algorithm, which was introduced by Chakuri Gupta and al. And basically, when an element arrives, we check whether or not to put this element inside our current solution. So we check whether the marginal contribution of this element E is worth 1 plus beta times the sum element E prime inside our current solution. And we do this swap to maintain feasibility, and this W E prime is just an upper bound on the actual contribution of this element E prime. So the analysis of this procedure reveals two facts. One, since we're running a streaming local search algorithm, we won't be able to do much better than the regular offline local search. So we lose some approximation here. The second loss is due to the the streaming procedure, because when we see an element, we're only able to check the marginal contribution of this element with respect to the current memory that we have, and not necessarily our final solution. However, what we lose during this can be upper bounded by this, what you see here, this 1 over beta times the difference between our final and initial solution via a more careful analysis. And this is actually what we can play with, because if we know, since this holds for any pass, if we know that this difference is, let's say, small, well, we can reduce the beta accordingly to yield some improvement. So the algorithm is actually quite simple. We just run this algorithm multiple times, and we set the parameter beta accordingly. Previous result were only consider this streaming-like version of this algorithm, but they were setting the parameters so that they would at some point yield some convergence, whereas here we optimize the beta on each pass. We also have an optimal memory because we only store k elements, and since those beta can be computed exactly for, let's say, a practical point of view, you can even have a faster convergence than the one we show. So this is it for the monotone case. I won't discuss the non-monotone case. There are the details in the paper, but basically we most of the analysis relies on the monotone case. So of course there are open question of whether we can improve upon in terms of approximability. There's only the cardinality constraints, which is known to be tight. We have hardness result, and so we have a matching lower bound between the best we can do and the hardness result. But outside of cardinality constraint, we don't know much. And one thing that I would find really interesting is relate the best theoretical guarantee we can obtain with the memory or the number of queries or the number of passes that we're able to do. For example, if we restrict ourselves with having k elements in our solution, maybe 1 over 4p is actually the best we can do, but we don't know that yet. So that's it for me, and thank you all for listening.
Thank you. We have time for a couple of questions.
Sure.
So people can unmute themselves and ask, or either on chat if you prefer that. So can you say a couple of words how you set these betas? Like, are they exponentially decreasing or something? Or?
No, they so it depends on two cases, whether or not it depends on the ratio between the let's say final and initial solution, and whether this this ratio is small or not. And we have two cases, and we kind of set them to be equal so that we have find the beta accordingly.
Okay, interesting. Yeah. So it's adaptive, like somehow based on, it's not fixed in advance.
No, it's not.
So, yeah. Okay, any other questions? not, let's thank Theopile again, and maybe Bishramek can already set up, share the slides. Okay, maybe we can start. So the next talk will be by Shramek.
Can you hear me?
Yeah, it's good. So yeah, so next talk will be on LP pattern matching in a stream by Shremek Uznansky. So please go ahead, Shremek.
Okay, let me try to start the video, but if the bandwidth is too small, just tell me.
Okay, looks good so far.
Hi everyone. I want to talk about the joint work with Tania Starikowskaja and Michał Szwagerka. So our setting is a classical setting in a stringology, which is I give you a text and a pattern. A pattern is let's say shorter than a text, and they are over some abstract alphabet. And basically, what I asked to compute a distance between every substring of a pattern of a text to a pattern, or a substring of the same length, of the length of the pattern. And basically, this question is a generalization of a classical pattern matching question, because if the distance is 0, then we have exact match. But if the distance is greater than 0, maybe we are interested in like how much do they differ. So a couple of interesting metrics that you could define in this question is, let's say, a Hamming distance. So that would be counting the number of mismatches, of mismatched letters. Or if you introduce some numerical alphabets, then maybe Manhattan distance, so L1 distance, or Euclidean distance, so L2 distances, or maybe some general LP distance. So here, for example, for Hamming distance, at this offset, we have distance 2, and then you can just go on and see distance 3, 4, 2, 4, and so on. So, of course, the answer is outputting the distance for all of the possible offsets. And this problem has attracted, I mean, it has a long history already of more than 40 years of trying to get the right answers under various constraints. This is like a filler slide. Don't focus on this one too much, because this is for the offline problem. And we'll be moving to the streaming setting. So in the streaming setting, I first give you a pattern, and you can look at it and store some fingerprint or some sketch of the pattern. But your operating memory is much smaller than the size of the pattern, so you cannot even store the pattern fully. And then I give you a text, and I give you a text one letter at a time. And after every letter of a text, I ask you to output the distance between the current window and the pattern. So the goal is to, of course, achieve to use as little memory as possible, and also answer your queries as fast as possible. So preferably have some form of real-time output. So there are some challenges, of course, in this setting, because well, many techniques used in the offline setting do not adapt to a streaming setting at all. For example, most of the algorithms that I just quickly glanced over at the previous slide were using some form of convolution or fast Fourier transform, which does not adapt to a streaming setting at all. And also, if we just make a detour to a streaming setting and let's say look at all of the work on maintaining norms over the windows, they do not adapt to all of those sketching techniques. They do not adapt nicely to, let's say, sliding window when we are looking at the distance to a particular object. So, state of the art of the problem just for a Hamming distance is that ICALP 2016 there was a result that provided 1 plus epsilon approximation of Hamming distances, and the memory is roughly square root of n divided by some poly in epsilon, And time is 1 over poly of epsilon per letter. And then concurrently to our work, there was a very nice result by Chan et al. At Stock this year, where they got square root of n over epsilon to the 1.5 space and 1 over epsilon cubed time. And this was done in parallel to our work, and well, we have slightly worse space, slightly better time per letter. So, and the techniques that we used do not overlap almost at all. So, of course, what we do, we extensively use sketching. So sketching is, like, you can think of this communication complexity problem where we look at, like, there are two players, they look at objects, and they want to write short summaries of the objects and just send it to a decoder, and then the decoder can compute some function over those objects. So sketching in a streaming setting is challenging because, well, a sketch of a current window of last n letters of a text can look totally different from a sketch of just a window shifted by 1. So this is, of course, a challenge that you have to overcome. And trying to do it in some form of a naive way would already deteriorate to spending n memory. So what we actually do, we mentally partition the text in a streaming setting into blocks of length square root of n. And then we know that if a pattern is sliding over this text, then it roughly almost all of the pattern is covered by some full blocks. And there are only some small leftovers on the left and on the right side. So we have this prefix part, middle part, and the suffix part. And basically all of those are solved separately in our work. So suffix part is the most trivial part. We can just store everything explicitly. Because the blocks are of length square root of n, we can store the last explicit square root of n letters of a text. We can do the same for the pattern, do some pre-processing, and have a fast answer to those queries. For the middle part, we can be clever and store sketches of the blocks of a text and store square root of n sketches of almost full length parts of the pattern. So roughly n minus square root of n parts of the pattern. And always at least one of those will overlap with some nice sequence of blocks on the text side. And this also requires a little bit of carefulness, and then we can achieve square root of n memory over epsilon squared, where this 1 over epsilon squared comes from the actual size of the sketches for the Hamming distances. And then the prefix part is like the main theoretical contribution of the paper, because basically the problem is I give you a block of a text. You can look at it now, but you have to forget what's the inside of this block, and you have to write down some information that later, much later, you can answer queries of the form, here is a prefix, and just tell me what is the Hamming distance between the overlap of the prefix of the text with suffix of this block. And well, we use some subsampling techniques here. I will not go into the detail, but you can basically do some combinatorial reasoning about storing the longest possible overlaps that generate at most, let's say, 1 over epsilon squared mismatches, and do it for every possible level of subsampling of a text. So you keep all of the position, you keep half of the positions, and so on. And this, you can actually achieve almost a constant space and to be able to answer such prefix-suffix queries. And then you have square root of n of those processes going in repetition. So once again, we get square root of n over epsilon squared space here. I strongly encourage you to go into the details to the paper or to listen to the recording of my longer version of the talk. And I promised LP, not just L0, the Hamming distances. So here is the, well, part of the paper where we advertise the results. And essentially, it's only a start of the answering what is the complexity of the problem. For Hamming distances, we got some nice time, which already we were unable to get for other norms, and even for some norms, well, we were unable to get the same memory complexity. All of those results, they require, almost every result of those requires a different set of tools. We have going from stable distributions to subsampling to reduction between norms, and so on. There is like whatever you like, you can find there. Thank you.
Okay, thank you, Shrimak. Maybe time for one quick question, then we move to the next.
So I have a question. So are you assuming that we know the value of n beforehand?
Yes, at the pre-processing phase, you can look at the pattern, and the pattern is n, and the n is the length of the pattern. Text, you can assume that the text is of infinite length.
Okay, so n is a
yes, n is the length of the pattern. N is the length of the pattern. This is like the only parameter concerning size of your input.
Okay, yeah, thank you.
Is there also a lower bound of root n on space?
No, there is no lower bound. There is like a trivial lower bound coming from communication complexity, which is 1 over epsilon squared, and it comes from a communication complexity of just computing a single Hamming distance between two words in a communication complexity game.
Huge gap. Okay, thanks.
There is a huge gap.
Yeah, indeed. Yeah, we can take more questions after all the talks at 20 minutes from now. So maybe let's move to the next talk by Colin Burns on streaming complexity of SVMs.
Can you see?
Yeah.
Great. So I'll be presenting our work on streaming complexity of SVMs. This is joint work with Alex Andoni, Yili, Sepide Mahabadi, and David Woodruff. Okay, so SVMs are this very classic algorithm in machine learning, which aims to find a good linear classifier of data. So more precisely, you're given n data points, and the goal is to minimize this objective function, which I won't go into in detail, but just this more or less standard formulation. And this is an extremely well-studied problem, both in theory and in practice, but there's been extremely little work on SVMs in the streaming setting, which is what we consider here. Okay, and so more specifically, we assume we observe a stream of n data points, and we actually consider two problems. So the first is what we call point estimation. So at the end of the stream, given any set of parameters, we want to approximately output the value of a function corresponding to those endpoints, given those parameters. Okay, and the second problem, which is maybe what you care about in practice, but it turns out you can relate these problems. The second problem is optimization. So at the end of the stream, can you find a set of parameters, theta and b, that approximately minimize the function? Okay, can you actually find a good approximate solution? And so, of course, the goal is to minimize the space. You want to aim for sublinear space, and as usual, we want to make no distributional assumptions. Turns out it's much easier if we can make some distributional assumptions. But so those are the problems we focus on. So point estimation and optimization, we show a number of results. We show both upper bounds and lower bounds for both. And so I don't have time to go into detail sort of the proof techniques and ideas, but I'll try to go through the main results. But first, it's probably worth covering some of the baseline approaches. What are the trivial things you can do? So with point estimation, you can simply sample points from the stream. So if you sample 1 over epsilon squared points, then this gives you a plus minus epsilon approximation. Okay, just using those points to, then given the parameters, you can estimate the value of the function just using those sampled points. And a almost as naive algorithm for optimization is simple, in this case, 1 over epsilon points. And then you can actually just run stochastic gradient descent on those points, given the function. And this again gives you an additive plus minus epsilon approximation. And this is just a standard result for strongly convex functions. Okay, so these are sort of the numbers to keep in mind, that these are what we should, what we want to beat or see if we can't do better than. So for the first problem, point estimation, we show a few upper bounds. First of all, for when d equals 1, the d is the dimension of the x's. When d equals 1, we can get a multiplicative algorithm, 1 plus epsilon multiplicative algorithm, using a similar amount of space, something like 1 over epsilon squared space. On the other hand, we show that it's impossible to get sublinear space when d is greater than 1. And so for the rest of the paper, we focus on the additive case, getting an additive plus minus epsilon approximation. Okay, and so again, focusing on point estimation for t equals 1 and t equals 2, we can get much better algorithms. So for t equals 1, this is 1 over root epsilon. For t equals 2, this is epsilon to the minus 4/5. You can also do better than 1 over epsilon squared for general constant t, but it turns out that these are especially interesting cases because you can use these for optimization. These give better upper bounds for optimization as well. Okay. So of course, to complement this, we also show lower bounds. So for point estimation, we show 2. First of all, we show when d is small. Well, in general, we can show this lower bound of epsilon to the minus d plus 1 over d plus 3. If you just plug in d equals 1, this gives you epsilon to the minus 1/2. Okay, so this is tight for d equals 1. This matches the upper bound that we show, but there is a gap for d greater than 1. Moreover, when as d goes to infinity, this goes to something like this goes to 1 over epsilon. Okay, so this is not tight for high dimensions, and so we also show a different lower bound specifically for high dimensions, and this is basically 1 over epsilon squared. Okay, this means that naive sampling really is optimal for high dimensions, essentially. Okay, so those are our main results for point estimation. Going into optimization, as I alluded to before, it turns out that you can basically turn a point estimation upper bound into an optimization upper bound with pretty much the same dependence on epsilon. It's just a small flip in the space. Okay, for d equals 1 and 2, this means that, as I said before, you get epsilon to the minus 1/2 and epsilon to the minus 4/5 for point estimation in these two cases. And so this immediately gives you optimization algorithms for d equals 1 and 2 that beat stochastic gradient descent, which was sort of the baseline. Okay, so I guess the upshot is you can do better than naive algorithms in low dimensions at the very least. Okay. And so again, to complement this, we also show a lower bound for optimization. So ignoring some technical details, basically for d at least 3, you can show a 1 over root epsilon lower bound for optimization. Okay, and recall that stochastic gradient descent uses 1 over epsilon space. So there is a quadratic gap here. Yeah, and this doesn't quite match the epsilon to the minus 1/2 that we have for d equals 1 because it doesn't quite work in that case. But it's still suggestive that something in that range is optimal. Okay, so in conclusion, like I said before, you can do better than naive algorithms for both problems, point estimation and optimization in low dimensions. But you cannot do better than this naive algorithm of sampling for point estimation. And it's not clear for optimization. Okay, and so a couple open questions include, well, first of all, that this was all based on what are called linear SVMs, that's sort of the standard formulation. But there's this variant called kernelized SVMs, which I won't go into detail, but these are often used in practice. And so being able to extend some of these results to that setting would be interesting. And also, as I suggested before, just closing this gap, especially this gap between optimization in high dimensions, of epsilon to the -1/2 and 1 over epsilon. I think that's quite an interesting open problem. I mean, SGD is a very generic algorithm, and so this might be suggestive of other problems as well beyond just SVMs. Okay, so that's all I have. Does anyone have questions?
Thank you. Questions? We have time for questions. Okay, maybe if not, let's go to the next talk by Ainesh.
Okay, I'll share screen now.
So the next talk will be by Ainesh Bakshi on weighted maximum independent set of geometric objects and turnstile streams. Ainesh.
Okay, thanks, Nikhil. This is a joint work with Nadia Chaburkar from MIT and David Woodruff from CMU. Okay, so let's start with recalling the maximum independent set problem. Here we are given as input a graph G on vertices V. So we have n vertices and an edge set E. And the goal is to output the largest set of pairwise disjoint vertices. So they should not have any edge between them. In this example, the maximum independent set looks something like this. And this problem is notoriously hard to compute, even approximately, and Hastad showed like n to the 1 minus epsilon approximation hardness result for it. Okay, but anyway, let's consider a slight generalization of this problem called the weighted maximum independent set, where now each vertex comes with a weight, which is a positive number. And the goal is to find the largest weighted subset that is pairwise disjoint. So in our example from before, if these are the weightings, the maximum independent set now looks like this. And the thing to note is that for the same graph topology, the weighted maximum independent set can actually differ a lot. Okay, we don't focus on the maximum independent set problem in full generality and instead consider geometric objects. So what do I mean by that? So our input now is a set of n geometric objects, such as disks. And our goal is now to output the largest subset of disks that are pairwise disjoint. So it looks something like this. And it's easy to translate between this problem and maximum independent set on graphs because these objects actually induce the graph. So for each object, we can represent them as one vertex and then consider an edge between two objects if they intersect. Okay, so it's easy to see that this is a special case. And now, somewhat interestingly, the complexity of approximation depends on what the object we are considering is. And I'll get into this in more detail. Okay, so in our work, we consider mainly two objects. We focus on intervals on the real line and disks in the plane. And these have several applications, including scheduling and network design, map labeling, etc. Okay, so let me recap what is known about these basic problems in the offline setting. So for intervals, there is a really simple algorithm. It's almost like a folklore algorithm. I couldn't find any reference for it. And it does the following. It takes the intervals and it sorts them according to right endpoint. And then it just greedily picks the interval that ends first, starting from the left. Okay, so we start by picking this interval, discarding all intervals that intersect with it, picking the next one. And now we have the choice of picking either this interval or this interval, but clearly this one ends first. So we'll pick this one, discard this one, pick the next one, and so on. And this algorithm works is you can show that this is optimal. And for this for unit weights, and for arbitrary weights, you can extend this algorithm using a dynamic programming approach. And this is like the canonical example for dynamic programming in modern algorithms textbooks. Okay, so one thing to keep in mind is that neither of these algorithms can be implemented in streams, and that's something I'll get into next. But before that, what is known for disks? Well, it's known that it can be hard to approximate the maximum independent set of disks. It's also NP hard to do this for like other geometric objects in the plane, like line segments and squares. But there exists a PTAS for this due to Chan and Harper from 2012. And it extends to other fat objects like squares, but it does not extend to line segments. Okay, so now let's get into the streaming model. Here our input is now given to us one object at a time. So, some objects appear. And our constraint is that we only have polylogarithmic and n working memory. So where n is the number of objects that we have to deal with. Okay, but now our problem is a bit ill-posed because we cannot even store a maximum independence set in polylog n space because it could be much larger than that. So instead, we relax our goal and only focus on estimating the cardinality of the maximum independence set, in the weighted case outputting a weight of the maximum independence set. Okay. So what is known in the streaming model? So this problem was considered by Cabello and Perez-Lentero for insertion-only streams. Here, you're only allowed to insert elements or objects and not allowed to delete them. And for intervals, what they show is 3/2 approximation can be obtained in polylog space. And interestingly, doing any better than a 3/2 approximation requires omega n space, which is essentially storing the entire input. Okay, so that's really tight. Now our first result is to extend this to the weighted setting in insertion-only streams. And we show that you can also obtain a 3/2 approximation for arbitrary weights in roughly the same amount of space, even though adding weights to the problem can change the maximum independence set by a lot. Okay, so that is the first result. And more generally, we initiate the study of studying maximum independence set of these objects and turn-style streams. And what do I mean by that? Here, once you insert an object later in the stream, you can go ahead and delete this object. Okay, and what we end up showing is that a 2 approximation can be obtained for arbitrary weights in polylogarithmic space. Further, doing any better than a 2 approximation requires storing the entire input, even for unit weight intervals. Okay, so let me summarize what I just said in a table and point out a couple of things. So in insertion-only streams, the right answer happens to be 3/2. Whereas in tail-size streams, as this shows like a strict separation between these models, the right answer is now 2. And then another interesting characteristic of this problem is that when you go from unit weights to arbitrary weights, the approximation ratio remains the same. That is also something that we show. Okay. Let's go to disks now. And for disks, we give 8 times square root 3 over pi approximation, which seems a bit magical, and I'll explain where that's coming from. And this is the best known, or the best we could show, even for insertion-only streams. And again, we are able to handle arbitrary weights. The lower bound, on the other hand, is just a 2 approximation, which we get from the one-dimensional hardness. And let me tell you a bit about where this approximation ratio is coming from. So this approximation ratio is actually 4 times 1 over the circle packing constant. And there are some interesting connections on how that shows up. But very roughly, what happens is that we consider a packing of the plane, and then you can divide this packing into 4 equivalence classes such that each equivalence class has disjoint disks, and that's where this is coming from. But for a detailed explanation, I recommend looking at the paper or the longer talk. Okay, so I like to end with some open questions, and there are many of them. One open question is, what is the complexity of MIS for arbitrary length intervals in turnstile streams? So this is well understood for insertion-only streams, but we only give results for special cases. Another great question is to close the approximation ratio for disks, and also study other geometric objects that have received a lot of attention in the offline setting, including rectangles? And more generally, can we get dimension-independent approximation ratios for arbitrary, or like for spheres or cubes in RD? And in general, exploring this connection between packing constants and approximation ratio is a really nice direction. Okay, I'll stop here.
Okay, thank you, Anish. Yeah, we have time for questions.
I have one question. Would it make sense to, when studying approximate solutions, consider to relax the notion of independence by some form of scaling the objects?
I mean, intersection is scale invariant, right? Like, so I'm not sure, like if you scale the entire space, the intersections will not change, but if you like decrease the radius of the objects, maybe.
So I was thinking, like, compare yourself with an optimum for unscaled objects, but allow yourself the notion of, for your solution, the scaled objects. Would it make sense at all?
I guess you're suggesting like a bi-criteria guarantee, like if I have scale R and I compare myself to like R over 100 scale objects. Yeah, I think that would make sense. Yeah. At some point, this would be trivial, right? Like I could decrease the bi-criteria notion to be small enough such that everything is independent. And it's a nice question where the complexity lies in between.
Okay. Any other final questions? If not, maybe let's thank Anish and all the speakers in this session again. And thank you. So I guess we have the gather in 20 minutes.